Graphs are very powerful tools to help solve physics problems. So far, we've been talking about a constant force exerted over a given time interval. But forces are not always constant. Life isn't that simple. Most of the time, they're changing over time. For the baseball examples we took, we assumed the force of the bat was constant over the time interval. But in reality, it starts out very, very small as it makes the initial contact with the ball. It then rapidly rises to its maximum value, and then it will decrease as the ball leaves the bat. This would be a very difficult problem to handle without a graph. Now, we're still not going to represent the actual force of the bat on the ball precisely because you're going to need a little higher level math than what we're dealing with here. But we're going to give it a shot. We'll at least show the methodology that you can use. So we're going to start by representing a constant force over a time interval delta t and plot force versus time on a graph. We'll start by taking the example we've worked earlier, which is where we have a constant force over a certain time interval. And we're going to plot force on the y-axis or vertical axis and time on the x-axis. Here's your constant force, and it's been applied for a certain amount of time. Notice what we have here. We have a rectangle. The area under this graph would be the vertical height, which is f. The horizontal is delta t. So the area is just merely height times base, which is equal to force delta t, which equals I, which is our change in momentum. So by finding the area of this shaded piece here, we can find the change in momentum due to that force. A more realistic force over time, for example, the baseball explanation would go something like this. Well, hopefully a little more regular than that. Okay, and finding the area under here can either be done by integration if we had a smooth curve here instead of this rough one I drew. Actually, it would work a lot better over here, or by using numerical methods or approximations. But in any case, whatever shape we have, you take the area under that shape, and that will give you the impulse and the change in momentum. If the force is not constant, like this simple example, the problems we'll be given in AP1 can be broken up into solvable shapes. For example, the force could be like this, and then maybe it goes off like this, and then comes down. So in this case, you could find out the area of this rectangle, you could find out the area of this triangle here, and this rectangle, put them all together, and you have the change in momentum due to the time-varying force that acts like that. And we'll have a few problems for you to work out here right after this.